Hello students, here we will derive an expression for impedance. An expression for impedance with the help of phasor diagram in LCR circuit. First we will define phasor diagram. What is phasor diagram? Phasor diagram, it is very simple. It is a diagram representing alternating EMF, alternating electromotive force and current as the rotating vectors, as the rotating vectors with the phase angle with the phase angles between them, with the help of phasor diagram we will find impedance in LCR circuit. Here L is inductor, C is capacitor, R is resistance, and these three are connected in series. First we will draw its connection diagram. This is a inductor, it is denoted by L. Next this is a capacitor, it is denoted by C. Next this is a resistance which is denoted by R, and connections are in series, and the circuit is then connected with AC source. AC source E, which is equal to E naught sine omega t. This is the series circuit of LCR. Now let the potential cross inductor VL and potential across capacitor is VC, and potential across resistor is VR. Now I will draw phasor diagram. This diagram is also very simple. Suppose that this is a graph line, this is along x-axis, and along this line we represent current I due to VR, due to potential VR, and here we can write it as according to Ohm's law, V is equal to I naught R along this line, and along this line now this represent this R. Now along this we will draw a line, and VL taken along this side, and this is the point O, and VC is its direction है downward. Now VL makes an angle 90 degree with current I, and VC makes an angle minus 90 degree with the x-axis. Now suppose that we will find their resultant at point B. Suppose this is point B. Now we will draw two lines and we will find the value here according to the diagram. This will be the potential VR. This will be the potential VR because it is lie on VR is equal to I naught R, and this will be equal to, and now join the line with point B. Now if we have VR is equal to I naught R and voltage across R is in same with current. Voltage across R here, voltage across R is in phase with current. Phase with current means there is no angle in the voltage and current, but in this case this is phi, this is the phase, this is the phase, and VL is equal to this VL will be equal to I XL, and VC is equal to I naught XC. But in case of this point, according to this, voltage across conductor VL leads the current by 90 degree. Here VL leads the current by 90 degree, means plus leads, but here angle is negative, therefore VC lags behind the current, lags behind the current. Lags behind means negative value with this current line. Now there are two values, therefore one VL and one VC. Suppose that net reactive voltage is VL minus VC if VL is greater than VC, and it can be also VC minus VL if the value of VC is greater than value of VL. But here we will represent the resultant value, total resultant value here, which is equal to VL minus VC, and this value, suppose this point is A, AB is equal to O, this value is D, and this point is E, this point is E. Therefore, AB is equal to, here AB is equal to OD. The value will be equal to this. Now, in a right angle triangle OAB, or in a parallelogram OABD, resultant of OA, resultant of OA and OD, this is OD value, is given by diagonal OB of the parallelogram OABD. Now, from this figure, OB will be equal to, from this figure, OB will be equal to under root, this is according to Pythagoras law, O square plus OC square. But now we will put the values of OB. The value of OB is E naught. It is E naught. Therefore, E naught is equal to value of OA, which is equal to VR. Value of OA, which is equal to VR square, plus value of OC, sorry, OD. Here is OD. OD is equal to AB. The value is equal to AB is equal to OD equal to VL minus VC square. Now we will put the values. VR is equal to I naught R. VL is equal to I naught XL. VC is equal to I naught XC. Here, these three terms are according to Ohm's law, which is equal to V equal to IR, and this value can be written as under root I naught R square plus I naught XL minus I naught XC square, and now I naught can be taken as common. I naught here common, and this is equal to R square plus XL minus XC square, which is the value of E naught. E naught is equal to I naught under root R square plus XL minus XC square, and from here we get, taking this is under the E naught, E naught divided by I naught. This term will be divided on the left hand side, which is equal to under root r square plus xl minus xc square. But in LCR circuit, effective resistance, effective total resistance which is called impedance, called impedance, denoted by Z. Therefore, this Z will be equal to E naught divided by I naught, which is equal to, we know that we have solved, R square plus XL minus XC square. Therefore, Z is equal to R square plus XL minus XC square. This is the derivation of impedance in LCR circuit. Now here some further cases, that from figure we have tangent phi in a figure. From phasor diagram we have, from phasor diagram we have tangent phi is equal to OA divided by, sorry, AB, here AB divided by OA, perpendicular upon base, and perpendicular's value is VL minus VC divided by VR, and here put the value of again, this is equal to I naught XL minus I naught XC divided by I naught R. From here we will get this, cut this common with denominator, which is equal to XL minus XC divided by R. Therefore, we calculate tangent phi as XL minus XC divided by R. First, number one case. Number one case is, if XL is equal to XC, if XL is equal to XC, put this value here, then we will get tangent phi equal to 0, therefore phi will be equal to 0. It means that voltage and the current are in same phase. It means that voltage and the current are in same phase, phi, which is equal to 0. Second value is, for second, If suppose that this term is, which here is xl minus xc, this term is positive, xl greater than xc, then tangent phi will be positive, therefore phi will be positive. Hence voltage leads the current by phase angle phi. Here voltage leads the current. Here voltage and current are in same phase, but here voltage leads the current by phase angle phi. And third case is if xl is negative, xc, therefore tangent phi will be negative, therefore phi will be negative. This show that voltage lag behind, voltage here leads but here lags behind the current by phase angle phi. Now here one point is more, which is resonance. I will solve it here. Resonance. It is the important point in this LCR circuit. It means that current is maximum if impedance is least. Current is maximum if impedance Z, or it is in net resistance also, it is impedance is least. Therefore the value of this impedance will be least if this term will be equal to 0. This term x L minus xc equal to 0. Therefore xc is equal to xl. But we know that xc is equal to, this implies xc is equal to 1 upon omega c, and xl is equal to omega L, and from here we will get multiply this term omega with omega and L with c, and we will get omega square is equal to 1 upon LC. Therefore omega will be equal to 1 upon under root LC. But we know that omega is equal to 2 pi into mu. Omega is equal to 2 pi into mu, which is equal to 1 upon under root LC. Now taking this term towards right hand, and we will get frequency is equal to 1 upon 2 pi under root LC. This is the resonance frequency of LCR circuit. Here XL, XC. XC is the reactance of capacitor, which is equal to 1 upon omega c, and XL is the reactance of inductor, which is equal to omega L. In both cases omega is equal to 2 pi upon capital T, and which is equal to 2 pi into 1 upon t. T is time period. which is equal to 2 pi into mu, which is the frequency. So we have put here the value of omega is equal to 2 pi mu. It is the whole derivation regarding LCR circuit. First, this is the impedance, and these are the 3 points according to this term, because this is k term. Here it can be 0, it can be positive, it can be negative. When two terms are equal, then phi equal to 0, it means voltage and the current are in same phase. Voltage and the current are in same phase. If XL is greater than XC, then this value is positive. Tangent phi greater than 0, it means phi greater than 0. For positive value, voltage leads the current by phase angle phi. In phasor diagram, this is positive value of phi. This is the positive value of phi, and here this is the negative value of phi. If VL is greater than VC, value will be positive. If VC is greater than VL, value will be the negative. Same here, it is explained. If XL is less than XC, then tangent phi negative. Therefore, voltage lags behind, means negative. Negative value of phi, the current by the phase angle phi. And the resonance term is in which the term current maximum if Z is least. Z means impedance is least. If impedance is least, this value will be equal to 0. From here, these two terms equal, and then we put the values of XC and XL here. After simplification, we get the resonance frequency mu is equal to 1 upon 2 pi under root LC. Thanks for watching.